Good evening, and welcome to today's episode. If you're listening to this, you've probably come here too. Let your thoughts drift gently across cosmic distances to allow your mind to float softly through space and time, settling into the quiet vastness where stars burn patiently and galaxies spiral slowly through the dark. You're in the right place. Tonight's journey takes us through 100 gentle facts about the universe, each one a small window into the cosmos. The universe stretches beyond imagination, older than comprehension, filled with wonders that glow softly in the darkness. From the smallest particles to the largest structures, reality unfolds in layers of quiet complexity. What better way to drift toward sleep than by counting cosmic facts instead of sheep? Now, before we float too far into the void, I should mention that trying to list 100 facts about anything is the universe's way of testing patience. Hopefully it tests yours just enough. Before we begin, I'd love to know where in the world you're listening from. It always touches me to see these quiet journeys reach so many corners of the globe. Each of you a small consciousness contemplating the whole. If you enjoy these calm explorations, please give the video a like and subscribe to the channel. It really helps others find this peaceful corner of science. To those already subscribed, thank you. Your support means the world, or perhaps the universe. Please also click the notification bell so you won't miss the next quiet adventure we take together. I do hope this video isn't too interesting that it keeps you awake. But if it does, at least you'll drift off having learned something quietly wonderful about the cosmos that holds us. So, settle in, relax, let your shoulders drop, and allow your mind to drift gently outward into the space between stars. Let's begin tonight's exploration. What does it mean to know 100 things about infinity? Chapter 1. The beginning. Let's drift gently into the story of beginnings. The universe started somewhere, somehow, 13.8 billion years ago, give or take a few hundred million. Everything that exists emerged from something impossibly small, unfolding slowly into the vast cosmic tapestry we inhabit. It's a story written in light and gravity, in the gentle expansion that continues even now. The universe began with the Big Bang, though that name feels almost too violent for something that was really just space itself beginning to exist. Time starting its patient tick forward. Before the Big Bang, there was no before, no space to contain anything, no time for events to unfold. Imagine the 19th century, when people assumed the universe was eternal and unchanging. Then, Edwin Hubble observed that distant galaxies were moving away from us. Their light stretched toward red by the expansion of space. Georges Lemma, Trey, a Belgian priest and physicist, proposed that if everything was expanding, running the clock backward meant everything must have emerged from a single point. There's something quietly profound about how the entire universe has a birthday. How everything shares a common origin. Think of it like a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. Not because the raisins are moving through the dough, but because the dough itself is growing. Not literally bread, but close enough to feel the gentle expansion. The universe is approximately 13.8 billion years old. Determined by measuring the cosmic microwave background radiation, the afterglow of the Big Bang still detectable today. Space itself is expanding, carrying galaxies apart like leaves on a flowing stream. This expansion doesn't have a center. Every point in space sees every other point receding, as if the universe is expanding from everywhere at once. The Big Bang wasn't an explosion in space, but an expansion of space. Reality itself unfurling like a flower opening in time-lapse. Petals spreading slowly outward forever. Picture a balloon with dots drawn on its surface. As you inflate the balloon, every dot moves away from every other dot, though none occupy a special position. That's cosmic expansion. Space stretching uniformly, distances between galaxies growing not because galaxies move, but because space itself grows between them. The fabric of reality gets bigger, pulling everything along. The early universe was incredibly hot and dense, filled with a soup of particles and radiation too energetic for atoms to form. As expansion continued, temperatures dropped, allowing protons and electrons to combine into hydrogen, the universe's first atoms, This moment, called recombination, happened about 380,000 years after the Big Bang. Before then, the universe was opaque, light scattering constantly off free electrons. After recombination, light could travel freely, and that ancient light still reaches us today as the cosmic microwave background, a faint glow in every direction, the universe's baby picture written in microwaves. Today, cosmologists study the Big Bang through multiple lines of evidence. The expansion of space, the cosmic microwave background, the abundance of light elements like hydrogen and helium matching Big Bang predictions. They've mapped fluctuations in the ancient radiation, tiny variations in density that seeded galaxy formation. Satellites like Planck and WMAP have measured these patterns with exquisite precision, revealing a universe 13.8 billion years old, flat in its geometry, composed mostly of mysterious dark energy and dark matter. Yet even with all we know, the moment of the Big Bang itself remains veiled. Quantum gravity effects making the first fraction of a second deeply mysterious. So perhaps that's why the Big Bang feels so quietly momentous. It reminds us that everything has a beginning, that the entire cosmos emerged from something smaller than an atom, that all of space and time unfolded from a single origin point. We too emerged from that ancient beginning, our atoms forged in stars, our existence possible only because the universe had a birthday. In that cosmic genesis, we find connection to everything. Proof that we're not separate from the universe, but temporary patterns in its ongoing unfold. Chapter 2. Cosmic distances from here. Our journey takes us into the vastness of space itself, the sheer scale of the universe. Light travels faster than anything we know. Yet cosmic distances are so enormous that light itself takes years, centuries, millennia to cross them. A gentle reminder that reality is larger than comprehension. The universe is incomprehensibly vast, measured in units that dwarf human experience. Light travels at 299,792 kilometers per second in vacuum, fast enough to circle Earth's equator 7.5 times in 1 second. Yet even at this speed, light from the sun takes about 8 minutes to reach Earth, covering the 150 million kilometer distance through empty space. Distances stretch infinitely. The nearest star to our sun, Proxima Centauri, lies about 4.24 light-years away, meaning light from that star takes 4.24 years to reach us. If you could travel at light speed, which you can't, you'd spend over 4 years crossing that gap. And that's our closest stellar neighbor. Most stars we see at night are hundreds or thousands of light-years distant, their light beginning its journey toward our eyes before recorded human history began. Imagine standing on a beach, looking at a grain of sand. Now imagine that grain represents our solar system, the sun and all its planets compressed to that tiny point. On this scale, the nearest star would be another grain of sand about 7 kilometers away. The Milky Way galaxy would stretch thousands of kilometers, containing hundreds of billions of grains, most of them separated by kilometers of empty space. That's cosmic scale. Distances so vast, they make the human mind feel pleasantly small. Think of it like looking at mountains on the horizon. They seem close enough to touch, yet reaching them requires hours of travel. Multiply that deception by billions, and you approach cosmic distance, where objects looking nearby are actually separated by voids so vast that light itself ages crossing them. Our Milky Way galaxy spans about 100,000 light-years from edge to edge, a gentle spiral of stars, gas, and dust, rotating slowly around a supermassive black hole at its center. The solar system orbits this galactic center once every 230 million years, drifting through space at about 220 kilometers per second, yet taking eons to complete a single revolution. The Andromeda Galaxy, our nearest large galactic neighbor, lies about 2.5 million light-years away, so distant that light, leaving it now departed before humans evolved. Back in 1995, astronomers pointed the Hubble Space Telescope at a seemingly empty patch of sky no larger than a grain of sand held at arm's length and exposed the image for 10 days. The resulting Hubble Deep Field revealed thousands of galaxies, each containing billions of stars, some so distant their light had traveled for billions of years to reach the telescope. It's humbling to realize that seemingly empty darkness contains multitudes, that everywhere we look, given enough patience, the universe reveals layer upon layer of structure, fading into distance. Today astronomers measure cosmic distances using various techniques. Parallax works for nearby stars, measuring how they appear to shift position as Earth orbits the Sun. Standard candles like Cepheid variable stars and type Ia supernova extend the distance ladder to millions and billions of light. The most distant objects detected lie over 13 billion light-years away, their light showing us the universe as it was less than a billion years after the Big Bang. The observable universe spans about 93 billion light-years in diameter, accounting for expansion during light's travel time. Though the entire universe might be infinite beyond what we can observe, perhaps cosmic distances whisper something gentle about humility. How the universe cares nothing for human scale. How vastness is built into reality's structure. We measure our lives in years, our histories in millennia, yet the universe counts time in billions, distances in trillions of kilometers, its patience exceeding comprehension. In that cosmic scale, we find not insignificance but wonder, proof that existence is far grander than our immediate surroundings suggest. Chapter 3. Stars and Light. Let's drift into stars. Those patient nuclear furnaces, scattered through space. They burn quietly for millions or billions of years, fusing hydrogen into helium, converting mass into light through Einstein's famous equation. Stars are why we exist. Factories producing the elements that make planets and life possible. Stars form when clouds of gas and dust collapse under gravity, density increasing until the core becomes hot and dense enough for nuclear fusion to ignite. Hydrogen nuclei overcome their electromagnetic repulsion through quantum tunneling, fusing into helium and releasing energy. This fusion generates pressure that balances gravitational collapse, creating a stable equilibrium that can last billions of years. Nuclear fires burn slowly. Our Sun, a medium-sized yellow star, has been shining for about 4.6 billion years, and will continue for another 5 billion before exhausting its hydrogen fuel. It converts about 600 million tons of hydrogen into helium every second, yet contains enough fuel to maintain this pace for eons. The energy release travels slowly from the core outward, taking thousands of years to reach the surface as photons scatter through dense plasma. Then only 8 minutes to cross space to Earth. Imagine a candle burning in slow motion, so extreme that a human lifetime passes between flickers, each subtle shift in flame taking generations to unfold. That's stellar timescales. Processes so gradual, they seem eternal, yet everything changing if you wait long enough. Stars live, evolve, and die, just slowly. Think of it like a bonfire that burns for 1,000,000 years. Its fuel so abundant that generations of people could warm themselves without noticing any diminishment. Stars operate on scales where change is measured in millions of years, where patience is built into their nuclear hearts. Stars come in various sizes and colors, determined by their mass. Small red dwarfs burn their fuel so efficiently they can shine for trillions of years, longer than the current age of the universe. Massive blue giants burn hot and fast, exhausting their fuel in mere millions of years before exploding as supernova. Medium stars like our Sun will eventually expand into red giants, swelling to engulf inner planets before shedding their outer layers, and collapsing into white dwarfs, dense stellar cores supported by electron pressure rather than fusion. Back in the early 20th century, Cecilia Pingaposhkin discovered that stars are composed mainly of hydrogen and helium, contradicting the assumption that stars had similar composition to Earth. Her PhD thesis, proposing this hydrogen-helium dominance, was initially dismissed by prominent astronomers who thought it impossible. Years later, her conclusion was proven correct, revolutionizing stellar astrophysics. It's touching how a young woman's insight, initially rejected, became fundamental to our understanding of stars. Proof that patient truth eventually outshines dismissive certainty. Today, astronomers classify stars using spectroscopy, studying the light they emit to determine composition, temperature, and motion. They've discovered that stars have life cycles, forming in nebulae, burning through various fusion stages depending on mass, then ending as white dwarfs, neutron stars, or black holes, The Hertzsprung-Russell diagram maps stars by luminosity and temperature, revealing distinct populations. Main sequence stars fusing hydrogen, red giants burning heavier elements, white dwarfs cooling slowly over eons. Binary and multiple star systems are common, gravity-binding stars in orbital dances lasting millions of years. There's something quietly poetic about stars, how they transform simple hydrogen into complex elements through patient fusion, how they shine for eons without complaint, how their light carries stories across cosmic distances. We too burn our inner fuel, converting potential into presence, shining briefly against darkness. In that stellar persistence, we find inspiration, proof that steady burning over time accomplishes what brief intensity never could. Chapter 4. Galaxies and structures. Now we turn to galaxies. Vast islands of stars, bound by gravity into beautiful spirals, ellipses, and irregular shapes. Hundreds of billions of stars gather together, orbiting common centers, separated from other galaxies by enormous voids. The universe organizes itself into these structures, clustering matter across cosmic scales. Galaxies are gravitationally bound systems containing stars, gas, dust, and dark matter, ranging from dwarf galaxies with a few million stars to giant ellipticals with trillions. Our Milky Way is a barred spiral galaxy, arms of stars and nebulae winding outward from a central bulge and bar structure. The whole system rotating slowly around its core, islands in space. Spiral galaxies like ours feature flat disks with elegant arms where new stars form continuously, gas clouds collapsing under gravity, igniting fusion, illuminating the spiral structure. Elliptical galaxies are more rounded, containing mostly old stars, with little gas for new star formation. They are stars following elliptical orbits in 3 dimensions, rather than circling in a plane. Irregular galaxies lack defined structure, often distorted by gravitational interactions with neighbors, stellar nurseries scattered chaotically through their volumes. Imagine cities seen from an airplane at night, each one a cluster of lights separated by dark countryside. Some cities larger with clear structure, others smaller and scattered. That's how galaxies appear. Luminous structures separated by vast cosmic voids. Gravity organizing stars into recognizable patterns, while darkness fills the spaces between. Not quite cities, but the analogy carries a gentle truth about structure in emptiness. Picture sheets of soap film stretched across a wire frame. The film naturally forms surfaces and curves, thickening at edges and intersections, thinning elsewhere. That's how matter distributes in the universe, forming filaments and sheets with galaxies clustered along these structures. Vast voids lying between where little matter resides. The cosmic web, structure emerging from quantum fluctuations in the early universe, amplified by gravity over billions of years. Galaxies clustered into groups and clusters. Sometimes thousands of galaxies bound together by mutual gravitation. The Milky Way belongs to the local group, containing Andromeda, Triangulum, and about 80 smaller galaxies spread across about 10 million light. The local group itself sits on the outskirts of the Virgo a massive structure containing thousands of galaxies. Beyond lie even larger structures, superclusters, and filaments forming the cosmic web, the largest known structures in the universe, stretching hundreds of millions of light. Consider the work of Vera Rubin in the 1970s, who measured rotation curves of spiral galaxies and found something strange. Stars at galaxy edges orbited too fast, faster than visible matter's gravity could explain. They should fly apart, yet they didn't. Her observations provided strong evidence for dark matter, invisible mass comprising most of a galaxy's gravitational pull. Her patient measurements revealed that the universe contains far more matter than we see, that galaxies are embedded in massive dark matter halos extending well beyond visible stars. It's humbling to realize we've detected only a fraction of what exists, that most of the universe remains invisible, betraying itself only through gravitational effects. Today telescopes map billions of galaxies across cosmic time. The Sloan Digital Sky Survey has catalogued millions, revealing the cosmic web structure, how galaxies cluster along filaments with voids between. Hubble and James Webb Space Telescopes observe distant galaxies formed less than a billion years after the Big Bang, showing how galaxy structure evolved over cosmic time. galaxies merge and interact. Gravity pulling them together, triggering star formation, creating beautiful shapes before settling into new equilibrium configurations. The universe is dynamic, constantly rearranging its structure over timescales of millions and billions of years. Perhaps galaxies teach us about community, how individual stars gather into larger structures, how gravity binds separate entities into coherent wholes, how even vast distances don't prevent connection. We to cluster, forming families, communities, civilizations, drawn together by forces we don't fully understand. In that galactic clustering, we find patterns that echo across scales, proof that the universe organizes itself. That structure emerges from emptiness. That separation and gathering are both fundamental rhythms of existence. Chapter 5. Black holes and gravity gently. We move toward black holes, regions where gravity becomes so intense that not even light can escape. Space-time curves infinitely inward, creating one-way membranes called event horizons. Beyond these boundaries, causality points toward singularities, places where our physics breaks down. Black holes form when massive stars collapse after exhausting their fusion fuel, gravity overwhelming all other forces, compressing the stellar core to infinite density. The escape velocity at the event horizon equals the speed of light, creating a boundary from which nothing can return. Time itself behaves strangely near black holes, slowing relative to distant observers, stopping completely at the horizon from an outside perspective. Gravity curves everything. Imagine a whirlpool in a river, water spiraling inward toward a central drain. Objects floating nearby get pulled toward the center, first slowly, then faster as they approach, until they cross a point of no return and vanish down the drain. That's a black hole's gravitational pull, space-time itself flowing inward like water, carrying everything toward the singularity at the center. Not quite literal, but close enough to feel the one-way descent. Think of it like a deep well, so steep that any ball rolled too close slides inevitably downward, accelerating as it descends, unable to climb back out no matter how much energy it has. Black holes are wells in space-time itself, gravity creating slopes so steep that even light, the fastest thing that exists, can't escape once it crosses the event horizon's edge. Black holes come in different sizes. Stellar mass black holes form from massive star collapse, ranging from a few to tens of solar mass. Supermassive black holes, millions or billions of times the sun's mass, lurk at the centers of most galaxies, including a 4 million solar mass giant at the Milky Way's core called Sagittarius A. Scientists don't fully understand how supermassive black holes formed, whether from direct collapse of massive gas clouds or through merger of many smaller black holes over billions of years. Back in 1915, Karl Schwarzschild found exact solutions to Einstein's newly published general relativity equations, describing what we now call black holes. Though the term wasn't coined until 1967 by John Wheeler, Einstein himself doubted black holes could actually exist in nature, considering them mathematical curiosities. Decades of theoretical and observational work proved him wrong. It's touching how even Einstein's intuitions had limits, how reality exceeded even his revolutionary imagination, how the universe proved stranger than the strangest predictions. Today we detect black holes through their effects on surrounding matter. Gas falling toward a black hole heats through friction, glowing brilliantly before crossing the event horizon, making black holes, paradoxically, among the brightest objects in the universe when feeding actively. Gravitational waves from merging black holes, detected by LIGO starting in 2015, provide direct evidence of their existence and allow measurement of their masses and spins. The Event Horizon Telescope captured the first image of a black hole's shadow in 2019, showing the dark silhouette of M87's supermassive black hole against glowing surrounding material. Perhaps black holes whisper something profound about boundaries, how some thresholds, once crossed, allow no return, how gravity can curve space-time into one-way paths, how the universe contains irreversible processes. We too face event horizons in life, decisions and moments that, once passed, change everything irreversibly. In that gravitational inevitability, we find not despair but acknowledgement that some changes are permanent, that the universe flows forward, that time and causality create structures even more binding than physical barriers. Chapter 6. Planets and Moons next. We'll explore planets and moons, the smaller bodies orbiting stars and planets, worlds of rock and ice, gas and liquid, each one unique, shaped by formation history, internal heat, atmospheric chemistry. Earth is just one planet among countless billions. Our solar system, one example of planetary architecture. Planets form from protoplanetary disks, clouds of gas and dust orbiting young stars. Particles collide and stick together, gradually building larger bodies through accretion. Rocky planets form in the inner system, where temperatures allow metals and rocks to condense. Gas giants form farther out, where ice and frozen gases accumulate, their gravity eventually capturing surrounding hydrogen and helium to build massive atmospheres. Worlds orbit quietly. Our solar system contains 8 planets. For rocky inner worlds, Mercury, Venus, Earth, Mars, and for outer giants, Jupiter, Saturn, Uranus, Neptune, plus dwarf planets, like Pluto, in the distant Kuiper belt. Each planet has its own character, from Mercury's cratered surface, baked by the nearby sun, to Neptune's deep blue atmosphere, whipped by winds faster than sound. Methane ice clouds, drifting through hydrogen skies. Imagine a family of siblings, each shaped differently by the same upbringing, each expressing their shared heritage in unique ways. That's the solar system's planets, formed from the same nebular disk, but diverging into distinct worlds through subtle differences in position, mass, and composition. Not quite familial, but close enough to feel the kinship. Picture beads strung on invisible threads, varying in size and color. Some close together, others widely spaced, all circling a central lamp. That's planets orbiting their star, held by gravity's invisible threads, each maintaining its path through space, some taking mere months to complete orbits, others requiring centuries, yet all following elliptical paths described by Kepler's laws, dancing to Newton's gravitational tune. Moons orbit many planets, from Earth's single large moon to Jupiter's dozens, some as small as boulders, others larger than Mercury. Our moon formed about 4.5 billion years ago, likely from debris ejected when a Mars-sized body collided with the early Earth, material coalescing in orbit before solidifying into the spherical companion we see today. Jupiter's moon Europa harbors a subsurface ocean beneath its icy crust, kept liquid by tidal heating from Jupiter's gravity. Saturn's Titan has lakes of liquid methane and ethane, clouds of organic compounds, a thick atmosphere hiding its surface. Consider the discoveries of the Kepler Space Telescope, which from 2009 to 2018 stared at a single patch of sky, monitoring over 500,000 stars for the subtle dimming caused by planets crossing in front. Kepler discovered thousands of exoplanets, worlds orbiting other stars, revealing that planets are common throughout the galaxy. We now know of planets orbiting in habitable zones where liquid water could exist. Super-Earths larger than Earth, but smaller than Neptune. Hot Jupiters orbiting impossibly close to their stars. Systems nothing like our own. It's humbling to realize our solar system is just one configuration among countless variations, that planetary systems fill the galaxy, each unique yet following the same gravitational rules. Today, planetary science explores worlds through spacecraft and telescopes. Rovers trundle across Mars, analyzing rocks, searching for signs of ancient life. Probes have visited every planet in our solar system, revealing Jupiter's storms, Saturn's rings in exquisite detail, the ice geysers of the nitrogen plains of Pluto. Thousands of exoplanets have been detected and characterized, atmospheres analyzed for chemical signatures, orbits mapped, massas and radii measured. The search for another Earth continues. Patient scanning of stars for worlds that might harbor life. There's something quietly wonderful about planets. How gravity organizes matter into spheres. How each world becomes a unique expression of physical laws, playing out over billions of years. How moons dance around planets, as planets dance around stars. We live on one such world, a pale blue dot perfect for life. neither too hot nor too cold, blessed with liquid water and protective atmosphere. In that planetary fortune, we find not entitlement but gratitude, awareness that our world is both typical and precious, one of countless worlds, yet the only one we know that harbors life. Chapter 7. The elements. Let's drift into the elements. The building blocks of matter: hydrogen and helium, carbon and oxygen, iron and gold, each one forged in stellar furnaces or supernova explosions. Every atom in your body was created in a star, scattered through space when that star died, eventually collected into the cloud that formed our solar system. The universe started with only hydrogen and helium, the lightest elements, formed in the first few minutes after the Big Bang, when conditions were hot and dense enough for nuclear fusion. Everything heavier, from carbon to uranium, was forged later inside stars through nuclear reactions, or in the violent deaths of massive stars, when they exploded as supernova, or in collisions between neutron stars. We are stardust, literally. Stars fuse hydrogen into helium in their cores, releasing energy that makes them shine. As hydrogen depletes, stars hot enough begin fusing helium into carbon and oxygen. Massive stars continue the process, building neon, magnesium, silicon, finally iron. Iron is where fusion stops being energetically favorable. Fusing iron requires energy rather than releasing it. When massive stars develop iron cores, fusion halts, pressure drops, and gravity wins, compressing the core catastrophically before rebounding in a supernova explosion. Imagine a cosmic kitchen where simple ingredients combine under heat and pressure to create complex dishes. Hydrogen, the simplest ingredient, gets cooked into helium, then helium into carbon, each stage requiring higher temperatures, more extreme conditions, building heavier and heavier elements through patient nuclear cooking. Not quite cuisine, but close enough to feel the transformative process. Think of it like building blocks stacked together. Start with the smallest blocks. Hydrogen nuclei containing 1 proton. Stack 2 hydrogen blocks together. You get helium with 2 protons. Keep stacking under the right conditions. You build carbon with 6 protons, oxygen with 8, all the way up to uranium with 9. Stars are the builders, using fusions, heat, and pressure to stack protons and neutrons into increasingly complex nuclei. The heaviest elements, heavier than iron, form primarily in supernova explosions and neutron-star collisions. When massive stars explode, temperatures and neutron densities become so extreme that rapid neutron capture can occur, building elements like gold, platinum, and uranium in mere seconds. Neutron-star collisions, recently observed through gravitational waves and accompanying light, produce heavy element-rich ejecta that disperses through space, seeding future star and planet formation with atoms impossible to create through normal stellar fusion. Back in 1952, astronomer Cecilia Payne's colleague, Fred Hoyle, worked out the theory of stellar nucleosynthesis, showing how stars create elements through fusion. He predicted that carbon E, essential for life, must form through a precise resonance in helium fusion, a prediction later confirmed experimentally. Hoyle was also known for coining the term Big Bang somewhat mockingly while advocating for steady-state cosmology, a theory now abandoned. It's touching how even scientists who resist certain conclusions can make profound contributions, how truth emerges through collective effort despite individual biases. Today we detect elements in stars through spectroscopy, analyzing light to identify absorption lines corresponding to specific elements. Each element creates a unique spectral fingerprint, allowing identification of stellar composition across vast distances. We've traced the enrichment of elements over cosmic time: early galaxies containing almost pure hydrogen and helium, later generations enriched by successive stellar cycles. Our Sun contains about 2% elements heavier than helium, enough to build rocky planets and enable chemistry complex enough for life. Perhaps the elements teach us about inheritance and transformation, how simple beginnings lead to complex outcomes through patient processes, how what we are depends on what came before. Cycles of creation and destruction, building richness from simplicity. We're built from elements forged in long-dead stars, carbon in our cells, calcium in our bones, iron in our blood, all created through stellar alchemy. In that elemental heritage, we find connection to cosmic history, proof that we're not separate from the universe, but made from it. Temporary arrangements of stardust, contemplating its own origins. Chapter 8. Time and cosmology from here. Our journey takes us into time itself, the fourth dimension. The arrow pointing from past toward future. Time flows differently, depending on gravity and motion, relative rather than absolute, woven with space into a four-dimensional fabric called understanding time means understanding the universe's history and fate. Time began with the Big Bang, before which before has no meaning, no temporal dimension in which events could occur. Since then, time has flowed forward as the universe expands. Entropy increases, causality moves from past to future. The arrow of time points toward increasing disorder, though local regions can decrease entropy temporarily by exporting it elsewhere. Life being a prime example of local order maintained by increasing disorder in the time flows like rivers. Special relativity, formulated by Einstein in 1905, revealed that time is relative, flowing at different rates depending on relative motion. Moving clocks tick slower from a stationary observer's perspective, though the moving observer perceives their own time as normal. At speeds approaching light, time dilation becomes extreme. Years passing for stationary observers, while only days pass for travelers. Though such speeds remain purely theoretical for massive objects like spacecraft or people. Imagine two streams flowing down a mountain, one taking a straight, steep path, the other winding through gentler slopes. The straight stream reaches the bottom quickly, while the winding stream takes longer, covering more distance in the same vertical drop. That's time dilation through motion. Different paths through spacetime covering different amounts of proper time. Though all travelers agree on relativistic intervals, combining space and time, picture a rubber sheet stretched taut, with heavy balls placed on it, creating dimples and curves. A marble rolling across the sheet follows curved paths around the heavy balls. Its trajectory, bent by the sheet's curvature. That's general relativity's vision of gravity, mass curvings, other muscles, following curved paths through that warped geometry. What we perceive as gravitational attraction really being motion through curved space and time. General Relativity, published in 1916, showed that gravity affects time as well as space. Clocks closer to massive objects tick slower than clocks farther away, time itself dilated by gravitational fields. GPS satellites must account for this effect, their orbital clocks ticking slightly faster than ground clocks due to weaker gravity. Corrections necessary for accurate positioning. Time near black hole event horizons slows dramatically, approaching zero at the horizon itself from a distant observer's perspective. Though someone falling in would experience time normally until destroyed by tidal forces. Back in 1971, physicists Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial airlines, then compared them to reference clocks that stayed on the ground. The traveling clocks had aged slightly less than the stationary clocks, confirming special relativity's time dilation predictions with actual experiment. It is beautiful how something as abstract as relative time can be measured with sensitive clocks and airplane tickets. How the universe's deep principles manifest in tiny, measurable differences. Today, cosmologists use general relativity to model the universe's evolution from the Big Bang to present and into the future. The universe's fate depends on its energy content, the balance between matter, radiation, and dark energy. Current observations suggest dark energy dominates, causing accelerating expansion, implying the universe will expand forever. Galaxies receding until only the local group remains gravitationally bound. Stars eventually exhausting their fuel. Matter decaying over unimaginable timescales until nothing remains but dilute radiation in an ever-expanding, ever-cooling void. There's something quietly sobering about cosmic time. How the universe has a history billions of years long. How its future stretches trillions of years ahead. How human timescales are infinitesimal flickers in cosmic duration. We measure our lives in decades, our civilizations in millennia. Yet the universe counts time in billions of years, its patience exceeding comprehension. In that temporal vastness, we find not insignificance, but wonder, awareness, that existing at all, for however brief a moment, is the universe becoming conscious of itself, time itself contemplating its own flow. Chapter 9. Dark Matter and Dark Energy. Now, we turn to the universe's mysteries, the invisible components that comprise most of cosmic reality. Dark matter and dark energy, detected only through their gravitational effects, remain deeply puzzling despite decades of research. They remind us how much remains unknown. Dark matter is matter that doesn't emit, absorb, or reflect light, betraying itself only through gravitational influence on visible matter and light. It comprises about 27% of the universe's total energy density, far more than the ordinary matter making up stars, planets, and US. Galaxies rotate as if embedded in massive, invisible halos. Galaxy clusters contain far more gravitating mass than visible stars and gas can account for. Gravitational lensing, the bending of light by mass, reveals dark matter's presence through its effects on background light, invisible foundations. Dark energy is even more mysterious, comprising about 68% of the universe's energy density, causing the expansion of space to accelerate rather than decelerate as gravity would suggest. Discovered in 1998 through observations of distant supernova, dark energy behaves like a negative pressure permeating all of space, pushing everything apart, its density remaining constant even as space expands. Unlike matter which dilutes as volume increases, imagine a vast scaffolding made of invisible material, providing structure but impossible to see directly. That's dark matter, holding galaxies together, forming the gravitational skeleton along which visible matter accumulates, shaping the cosmic web, yet remaining stubbornly invisible to telescopes. Not quite scaffolding, but close enough to feel the hidden support. Think of it like an invisible river current pulling swimmers in directions they don't expect. They can't see the current, only feel its effects on their motion, inferring its presence from how it deflects their intended paths. That's how we detect dark matter, through its gravitational influence on things we can see. Invisible hands guiding visible matter through space. Picture a balloon, inflating, dots drawn on its surface, moving apart as the rubber expands. Now imagine the expansion accelerating over time, the rubber stretching faster and faster despite no additional air being pumped in. That's dark energy, causing the universe's expansion to speed up, empty space somehow pushing against itself, creating more space between galaxies at an ever-increasing rate. The nature of dark matter remains unknown despite extensive searches. Candidates include weakly interacting massive particles, WIMPs, which would interact only through gravity and a weak nuclear force, making them nearly impossible to detect directly. Axions, hypothetical particles predicted by certain extensions of particle physics, could also account for dark matter. Modified gravity theories propose that our understanding of gravity breaks down at galaxy scales, though most evidence favors actual invisible matter over modified laws. Dark energy is even more puzzling. The simplest explanation is a cosmological constant, a property of space itself contributing fixed energy density to every cubic meter of vacuum. Einstein introduced such a constant in 1917 to allow a static universe, later calling it his greatest blunder when Hubble discovered cosmic expansion. Now dark energy seems to require exactly the kind of term Einstein discarded, though its value is vastly smaller than quantum field theory predicts. A discrepancy of 120 orders of magnitude, one of the worst predictions in physics history. Consider Fritz Zwicky in the 1930s, studying the Coma galaxy cluster, and finding that galaxies move too fast for the cluster S visible mass to hold them together. He proposed Dunkelmaterie, dark matter, to explain the discrepancy. His contemporaries largely ignored him, his personality being abrasive and his conclusions seeming outlandish. Decades passed before Vera Rubin's work on galaxy rotation curves provided independent evidence, finally vindicating Zwicky's insight. It's touching how scientific truth emerges through patience, how dismissed ideas sometimes prove correct, how the universe keeps secrets that reveal themselves slowly through careful observation. Today, physicists search for dark matter through multiple approaches. Deep underground detectors wait for dark matter particles to collide with atomic nuclei, hoping to catch rare interactions. Particle accelerators, like the Large Hadron Collider, attempt to create dark matter particles in high-energy collisions. Satellites and telescopes map dark matter's distribution through gravitational lensing, revealing how invisible mass warps. Despite extensive efforts, dark matter particles have not been directly detected, the mystery persisting. Dark energy studies focus on measuring cosmic expansion history through distant supernova, baryon acoustic oscillations in galaxy distributions, and cosmic microwave background fluctuations. These observations confirm that expansion is accelerating, that dark energy exists in some form, but reveal little about its fundamental nature. Theorists propose various explanations, from vacuum energy to quintessence fields, that vary over time, yet no theory fully explains why dark energy has the specific value observed. Perhaps dark matter and dark energy teach us humility, how much of the universe remains invisible and incomprehensible. How our theories explain only a small fraction of cosmic reality, how mystery persists at the deepest levels despite centuries of scientific progress. We've mapped galaxies, measured the universe's age, peered back to nearly the Big Bang itself, yet most of what exists remains hidden, detectable only through indirect effects. In that cosmic mystery, we find not frustration but wonder, proof that the universe still has secrets to reveal, that knowledge is a journey without end, that embracing uncertainty is as important as seeking answers. Chapter 10. Deep Dive, the Cosmic Microwave Background. Let's drift deeper into the cosmic microwave background, the ancient light filling all of space, the afterglow of the Big Bang itself. This radiation, discovered accidentally in 1964, provides our clearest window into the early universe. A baby picture of the cosmos, taken when it was only 380,000 years old. The cosmic microwave background formed during recombination, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, photons scattering constantly off free electrons, light trapped in an endless pinball game. After recombination, photons could travel freely through transparent neutral gas, beginning journeys that continue today, reaching our telescopes as faint microwave radiation after traveling for 13.8 billion years. Ancient light whispers everywhere. Picture a dense fog lifting at dawn. Before the fog clears, you can't see far, light scattering in all directions. Visibility limited to a few meters. As the fog dissipates, suddenly you can see 4 kilometers, light traveling unimpeded from distant objects to your eyes. That's recombination, the universe's fog of free electrons clearing, allowing light to stream freely through space for the first time. That freed light still reaching us today as the cosmic microwave background. It's like hearing an echo from the beginning of time. The universe at recombination glowed at about 3000 Kelvin, a dull red heat. As space has expanded by a factor of about 1100 since then, the wavelengths of this radiation have stretched by the same factor, shifting from visible red light to microwave radiation with a temperature of 2.7 Kelvin, just above absolute zero. The entire sky glows faintly at this temperature, a uniform bath of ancient photons preserved from the universe's youth. Imagine taking a photograph of something very far away, so far that light takes billions of years to arrive. By the time the light reaches your camera, whatever you photographed has changed completely, aged billions of years, but the photograph shows how it looked back then, preserved in light. That's the cosmic microwave background. A photograph of the universe at 380,000 years old, showing structures that would later grow into galaxies and clusters, preserved in the patterns of slight temperature variations across the sky. Think of a canvas, painted with incredibly subtle variations. Most of it one color, but with tiny patches slightly warmer or cooler, differences of only a few millionths of a degree. That's the cosmic microwave background's temperature map. Nearly uniform, but containing tiny fluctuations, hot and cold spots that correspond to density variations in the early universe. Regions slightly denser than average that would eventually collapse under gravity to form galaxies. The cosmic microwave background was discovered by Arno Penzias and Robert Wilson in 1964 while working at Bell Labs. They were testing a sensitive radio antenna and kept detecting annoying background noise they couldn't eliminate. They cleaned pigeon droppings from the antenna, checked all equipment, yet the noise persisted, coming equally from all directions in the sky. Eventually they learned that Princeton physicists had predicted exactly such radiation as a relic of the Big Bang. The noise was the cosmic microwave background, the most important cosmological discovery of the 20th century, found while trying to eliminate what seemed like equipment malfunction. Satellites have mapped the cosmic microwave background in exquisite detail. COBE in the 1990s confirmed its blackbody spectrum and detected temperature fluctuations. WMAP from 2001 to 2010 mapped these fluctuations precisely, determining key cosmological parameters. Planck from 2009 to 2013 provided even finer detail, revealing the universe's geometry is flat. Its age is 13.8 billion years. Its composition includes 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. These measurements, extracted from subtle temperature patterns in ancient light, represent cosmology's triumph, precision understanding of the universe's fundamental properties. The temperature fluctuations in the cosmic microwave background correspond to quantum fluctuations in the very early universe, amplified by cosmic inflation, then imprinted on matter and radiation during denser regions appear slightly warmer. There's stronger gravity compressing matter and heating it subtly. Less dense regions appear slightly cooler. These tiny differences, parts per million, seeded all structure we see today. Galaxies forming preferentially in initially denser regions, voids developing where matter was slightly sparse. Scientists also study polarization patterns in the cosmic microwave background, which encode information about gravitational waves from inflation and the reionization of hydrogen billions of years later. Detecting primordial gravitational wave signals would confirm cosmic inflation and probe energy scales inaccessible to particle accelerators, revealing physics from the first tiny fraction of a second after the Big Bang. So the cosmic microwave background is really about time travel through light, how photons preserve information from the universe's youth, how looking outward in space means looking backward in time, how the universe's entire history is written in radiation, filling the sky. Every direction we look, we see the same ancient glow, the universe at 380,000 years old, surrounding us in all directions. Our observation point at the center, not because we are special, but because light from recombination reaches us from all directions equally. We're seeing the surface of a vast sphere, centered on our location simply because light takes finite time to travel. Perhaps the cosmic microwave background teaches us about memory and preservation, how the universe keeps records of its past in light itself, how ancient events leave traces detectable billions of years later, how information persists even as structures transform. We too carry echoes of our past, patterns formed in youth that persists into age. Early experience is shaping who we become. In that cosmic preservation, we find connection to beginnings, proof that origins matter, that understanding where we came from illuminates where we are, that the universe's baby picture contains seeds of everything that follow. Chapter 11. Philosophy, what the universe teaches us. Beyond the facts and figures, the measurements and theories, what does contemplating the universe teach us about existence, about meaning, about our place in the vast cosmic tapestry? These questions drift beyond science into philosophy, yet understanding the universe inevitably leads us to confront them. First, the universe teaches us about scale and perspective. We live on a small planet orbiting an average star in an ordinary galaxy among hundreds of billions of galaxies spread across billions of light. Our entire existence occupies a tiny sliver of cosmic time, a brief moment in a story billions of years long with trillions more ahead. This doesn't diminish us, but contextualizes us, revealing that we're a part of something incomprehensibly vast and ancient. We too need perspective, stepping back from immediate concerns to see larger patterns, recognizing that our problems, however pressing they feel, are temporary fluctuations in longer arcs. The universe's immensity invites humility, a gentle reminder that we're not the center, that existence is bigger than our experience of it, that countless other worlds likely harbor their own stories under alien stars. Think of it like looking at a tapestry from inches away, seeing only individual threads. then stepping back to see the entire image, how each thread contributes to a larger pattern invisible from too close. That's cosmic perspective. Our lives individual threads in a vast weaving, meaningful both in themselves and as parts of something larger. Second, the universe teaches us about connection and heritage. Every atom in our bodies was forged in stars or the Big Bang, scattered through space, eventually collected into the cloud that formed our solar system. We're literally made of stardust, our material substance sharing origins with everything else. Our very atoms cycled through countless configurations before becoming temporarily arranged as conscious beings. This physical connection extends to relationship. Gravity binds planets to stars, stars to galaxies, galaxies to clusters. Light connects distant objects, photons carrying information across cosmic voids. Quantum entanglement links particles. Regardless of separation, the universe is fundamentally interconnected, nothing truly isolated, everything participating in larger networks of relationship and influence. It's like a vast family tree, where everyone is related if you trace back far enough. Connections becoming clear when viewed across long enough timescales. We're cousins to stars, siblings to planets, descendants of the Big Bang itself. Our heritage cosmic rather than merely terrestrial. Third, the universe teaches us about change and impermanence. Stars are born, shine for billions of years, then die. Galaxies merge and transform. The universe itself expands and evolves, never static, always becoming. Nothing lasts forever in its current form. Yet nothing is truly lost either. Matter and energy transforming endlessly into new configurations. We too are temporary. Our lives brief flickers in cosmic duration, yet we participate in something ongoing. The atoms that make us will return to cycles of creation and destruction, becoming parts of other things, other beings, perhaps. The universe endlessly recycling its substance. There's peace in accepting, recognizing that our temporary existence doesn't diminish its meaning but locates it within a larger context of constant transformation. Perhaps this is like waves on an ocean. Each wave arising, cresting, then dissolving back into the sea. Unique, yet never separate from the water that forms all waves. We're waves of organized matter. Temporarily distinct, yet never separate from the cosmic ocean that birthed us. Fourth, the universe teaches us about mystery and limits. Despite centuries of scientific progress, we still don't know what dark matter or dark energy are, how the universe began, whether other universes exist, what consciousness is, whether we're alone. Some questions might have answers we'll eventually discover. Others might be fundamentally unanswerable, and distinguishing between them remains difficult. The universe reminds us that knowledge is partial, that certainty is rare, that embracing uncertainty is honest. Science progresses by acknowledging ignorance and working to reduce it, not by pretending we know more than we do. The most profound scientific statements often begin with, "We don't know," recognition that mystery persists at the deepest levels. In the end, what the universe really teaches us is that existence is wondrous beyond comprehension. That reality operates on principles both elegant and strange, that we're privileged to exist at all in a cosmos that seems indifferent, yet enables our presence. We're the universe becoming conscious of itself. Matter organized temporarily into patterns capable of contemplating their own origins, asking questions about meaning and purpose. The universe doesn't provide answers to those questions, doesn't tell us how to live or what to value. It simply exists, unfolding according to physical laws, indifferent to our interpretations. Yet in that indifference we find freedom, space to create our own meanings, to choose our values, to decide what matters within the brief span of awareness we're granted. What the cosmos teaches us is that we're small yet significant, temporary yet connected, isolated yet part of everything, mortal yet participating in something eternal. It invites us to hold these paradoxes gently, to find peace in our uncertain position, to live with wonder despite not having all answers, to recognize that being here at all, for however brief a time, is the universe's gift to itself. Closing. So here we are, at the gentle close of our drift through 100 facts about the universe. A journey measured not just in facts, but in feelings, not just in knowledge, but in wonder. Not just in understanding, but in appreciation for how much remains mysterious. We've floated through cosmic beginnings and vast distances, stars and galaxies, black holes and planets, elements and time, dark matter and dark energy, and the ancient light filling all of space. We've touched on 100 different aspects of the cosmos, each one revealing the universe as vast, ancient, dynamic, and deeply interconnected. From the smallest particles to the largest structures, from the Big Bang to the distant future, reality unfolds in patterns both elegant and strange. The universe teaches us that scale is relative, that connection runs deeper than separation, that change is constant, that mystery persists at the deepest levels, despite our progress in understanding. Why contemplate the universe at all, especially while drifting towards sleep? Because doing so places us in context, reminds us that we are part of something far larger and older than our individual concerns, connects us to the deepest rhythms of existence itself. Looking up at stars or contemplating cosmic facts isn't escaping reality but engaging with reality's truest scale, where our problems seem smaller and our existence seems more precious, precisely because it's so temporary and improbable. We inhabit a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, many of those stars hosting planets, some of those planets likely harboring life. We live in a cosmos, 13.8 billion years old, with trillions more years ahead. A universe that emerged from quantum foam and will expand forever into cold darkness. We're built from elements forged in stellar cores. Our atoms cycle through countless forms before temporarily becoming us. We're conscious patterns in the cosmic tapestry, awareness briefly emerging from matter's dance. Perhaps the universe reminds us to hold our certainties lightly, to embrace mystery as fundamental rather than frustrating, to find meaning not in cosmic purpose, but in our brief opportunity to experience existence at all. We're accidents of chemistry on a random planet. Yet we're also the universe contemplating itself. Matter organized into consciousness, temporary but real. Somewhere in the vast distances between galaxies, light continues its patient journey through expanding space photons that left their sources billions of years ago, still traveling. Some of them destined to reach Earth, eventually others to wander forever through voids, never encountering anything but darkness. Stars continue their quiet burning, fusing hydrogen into helium, converting mass into light, shining for billions of years without complaint or purpose, simply following the physics that governs nuclear fusion and gravitational equilibrium. Black holes continue swallowing matter, event horizons expanding infinitesimally with each particle that crosses them. Galaxies continue their slow collisions, gravity pulling them together over hundreds of millions of years, stellar orbits reshuffling, new stars forming from compressed gas, old stars flung into different trajectories. The cosmic web continues evolving, structure growing denser in some regions, while voids grow emptier.